Hello and welcome to Physics with Amol sir. So this video is for class 12 and today we are going to start with a new chapter, that is chapter number 4, moving charges and magnetism. So far we have seen charges at rest, that is electrostatics, and we spoke about current electricity. Now in this chapter we are going to move to the concept of magnetism, and not just magnetism, we are going to talk about magnetism, okay, the reason that is it arises, and that is the moving charges. Okay, so it's a very interesting chapter because here we are going to see the relationship between electricity and magnetism. For a long time it was thought that magnetism is a separate topic and electricity is a separate topic, but scientists like Ørsted, scientists like Hertz, they saw that these things are actually interrelated. Okay, so this particular chapter we are going to see the interrelationship between electricity and magnetism. Okay, so let's begin. So till now you have heard of the concept of electric field. Now we will see another concept that is called as the magnetic field. Electric field we denote by the symbol of capital E, magnetic field we denote by the symbol capital B. And just like electric field, magnetic field is also a vector. Okay, now remember, magnetic field arises due to moving charges. Okay, electric field we know it arrives due, it exists due to charges. If you have any charged body, okay, any charged particle, that will create an electric field. But magnetic field will arise when a charged particle is moving with some velocity. Okay, that is the concept of magnetic field. To best understand magnetic field, imagine a small magnet. Okay, you have seen a bar-shaped magnet. So around a bar-shaped magnet there exists this particular magnetic field. If you bring any magnetic material, let us say some iron pin, okay, a steel pin, iron pin, if you bring it here, it will get attracted towards the magnet. It is because in this magnetic field there is a force that is being exerted on that magnetic particle. Okay, so just like electric fields, magnetic field also exerts force, but it exerts force on specific materials, that is only on magnetic materials. Okay, so that is the concept of magnetic field. And remember, magnetic field arises when a charge is moving. Okay, so moving charges gives rise to the magnetic field. So this phenomena was actually discovered by a Danish scientist, Hans Christian Ørsted. Okay, he saw that that if you pass an electric current through a wire, okay, and if there is a compass placed near that wire, that compass actually moved, which showed that the current flowing in the wire was actually producing a magnetic field. Okay, now one nomenclature we are going to follow in this chapter. That nomenclature is, of course we know that magnetic field has a direction. Okay, to understand the direction of magnetic field, one symbol we will use. For example, if we are imagining that the magnetic field is coming out of the page, okay, it is perpendicular like this, there we will put the symbol of dot. So that means if we say there is a magnetic field which is denoted by these dots, that means the magnetic field is perpendicular to this plane and it is coming outwards. Okay, and if we draw a cross will signify magnetic field is going inside the surface. So it is perpendicular to the surface and going in this direction, that is inside. Okay, so these are the this is the nomenclature we are going to follow. Now we will see what happens when a charged particle or a charge moves in a magnetic field. Okay, so let us imagine there is some magnetic field, let us denote it by the symbol B. Okay, there is a magnetic field and let us put these dots. Dots will signify the magnetic field is perpendicular outwards to the plane of this board. Okay, so there is a charged particle, let us say Q. This charged particle is moving in this magnetic field. Now remember, if a particle is moving, a charged particle is moving, there will be a force exerted on this particular particle. Okay, that force we'll call as magnetic force. Okay, now this magnetic force is given by, we will write it as FB. Okay, it is a vector. Magnetic force is given by Q multiplied by V cross B. Okay, Q is the magnitude of that charge which was moving. V is the velocity of that charge cross, you remember cross product we had seen in 11th class. So V cross B. B is the magnetic field. Okay. So this formula gives the magnetic force on a charged particle. Okay. Obviously you will see that if velocity is 0, the force will be 0. Okay. So if a charge is not moving in a magnetic field, if it is stationary, there is no magnetic force. But if it is moving with some velocity, the force acting on that charge is given by the formula Q into V cross B. This is the vector form. The magnitude will be given by FB is equal to QVB sin theta. Theta is the angle between velocity of that particle and the magnetic field. Okay. Of course, you can see that if velocity of the particle and magnetic field, they are making angle 0. Okay. In that case, sin theta will be 0 and the force will also be 0. But if the particle is moving with an angle of 90 degree, okay, this is how the particle is moving, then sin theta will become 1. We'll get maximum force given by QVB. So we can write the formula for magnetic force as FB is equal to QVB sin theta. Okay, or you can write B is equal to FB upon QV sin theta. SI unit of force is Newton, charge is Coulomb, velocity is meter per second. So from that you can find out a unit for magnetic field. Okay, so that you will get it as Newton per Coulomb meter per second. Okay, or it is actually called as Tesla. Okay, so the SI unit of magnetic field is Tesla. Okay, remember this, that is the SI unit. Tesla is denoted by the symbol capital T. There is a smaller unit which is called as Gauss. Gauss is actually 1 Gauss is equal to 10 to the power minus 4 Tesla. Okay, that is a smaller unit of magnetic field. Now imagine a charge is moving through an area where there is an electric field as well as a magnetic field. Okay, so there is some area where we have an electric field E and a magnetic field B. A charge is moving through this particular area. Now the force acting on that charge Q will be given by F is equal to, there are going to be two forces on it. One will be the electric force that will be due to the electric field, and plus there will be a magnetic force Fb that will be given by the magnetic field. Electric force that will be given by Q into E. I am sure you remember this, we have seen in the second chapter. So electric field is given by Q into E plus magnetic field we already saw, it is given by Q into V cross B. Okay, so this force, this total force, this is actually called as the Lorentz Force. The electric field plus the magnetic field. Of course, you can easily write it as Q into E plus V cross B. This is a better way to write the Lorentz force. So this force that you get here, Q into E plus V cross B, this is called as the Lorentz Force. Okay, remember this in exam for 1 mark you will be asked to write the formula. Next we are going to find a formula for magnetic force on a current carrying conductor. Okay, so let's see. So imagine we have a conductor of length L and cross section area A. Imagine there is a current I which is flowing through this conductor. This is placed in a magnetic field, okay, of B. Right? Our task is to find how much is the force that will be exerted on this conductor. So let's begin. So first we are going to imagine that small n is the number of charges, okay, per unit volume which are flowing. Okay, so what is small n? Number of charges per unit volume. Therefore, the total number of charges, that is capital N, that are flowing from one point to the another, we can write it as N into L into A. Because L into A is nothing but the volume. So, number of charges per unit volume into volume will give the total charges capital N. Let me write it as equation number 1. Okay, these are the total charges which are flowing. So, therefore, I can write that the magnetic force on this conductor FB will be equal to, if you remember the formula, it is Q into V cross D. Q means total number of charges. How many total number of charges we have? We have capital N multiplied by Q. Okay, Q is the charge of the magnitude of each charge. So N into Q, this will be the magnitude of total charge multiplied by Vd. I am sure you remember Vd is the drift velocity cross B. Okay, so the magnetic force on this conductor is given by capital N into Q into Vd cross B. Now we can substitute the value of capital N. We will write it as N L A Q Vd cross B. Okay, this is giving us the total force. Now try to recall the relationship between current, electric current and drift velocity. I am sure you remember this formula. I is equal to Ne AVD. Okay, this is nothing but we can write it as NQ AVD. Right? So using this relation I can write, I know that N into Q AVD, this is nothing but electric current. Right? So I can write this as equal to I cross IL cross B. And you will see that L we have given a vector form. So I get the magnetic force as I into L cross B. Okay, now why this L is getting a vector sign? Actually, this particular L, that is length, is not a vector. Okay, it is actually a scalar quantity. But we have given it a vector sign to show that it is in the direction of the current. Okay, in whichever direction the current is going, okay, it is that vector. So L cross B. Right? So therefore L is getting a vector sign. Remember, length is always a scalar, but here is a special case where length we have made as a vector. So what you get? You get the magnetic force as I into L cross B. So on this conductor, this much is the magnetic force that is acting. Next, we will talk about the motion of a charged particle in a magnetic field. Okay. So let us draw a magnetic field first. So I am sure by now you remember very well that if we have drawn these x's, that means the magnetic field is perpendicular and going inside. Okay, so this is a magnetic field that we are imagining. Now let us say a charge Q is moving perpendicular to this magnetic field, means it is going from down to up. Okay, it is moving along this plane, so that the direction of velocity and the direction of magnetic field are exactly 90 degrees. So what you will get? You will get the magnetic force as QVB. Okay, the sin theta component is removed here. Why? Because theta is equal to 90. So sin theta becomes 1. So F is given by QVB. And how do you find direction? You can find the direction by using the right hand thumb rule. Okay, so how do you use the right hand thumb rule? The particle is moving like this. Okay, this is the direction of velocity from down to up, and the magnetic field is going inside. So my fingers will curl like this, and this thumb gives the direction of the force. So there will be a force that will act on the charged particle. But what will happen is, this particle will not move here, because the moment it starts to turn, again there will be a magnetic field. There will be a magnetic field, there will be a magnetic force. Right? Because of that, what will happen is, the motion of this particle will not be a straight line, but it will actually inscribe a circle like this. Okay, getting the idea? So, whenever a charged particle is moving perpendicular to a magnetic field, it will actually move in a circular path, because this force, that is the magnetic force, will now act like a centripetal force on it. Okay. Sometimes this question is asked in the exam, that if a particle is moving perpendicular to the field, what will happen to its motion? It will actually form it will go in a circular path, remember. What will happen if it is not exactly perpendicular? Okay, if there is any component of velocity which is along the magnetic field, means we had imagined that the magnetic field was inside and the particle was moving down to up. Okay, if let us say the velocity had been slightly tilted, okay, there would be some component along B. In that case, the particle would not go in a circular path, it will follow a path like this. Okay, it is called as a helical path. You can imagine it like a spring. Okay, so if it is not exactly perpendicular, then the path of the particle would be a helix. Okay, remember, but if it is perpendicular, it will go in a circular path. So now we will consider a simple case. Simple case, that is, the particle is moving perpendicular to the magnetic field, hence it is moving in a circular path. Let r be the radius, small r will be the radius of that circular path. So we can say that in this case the magnetic force is actually acting like the centripetal force. So I can say Fc is equal to Fb, Fc being the centripetal force. And we know the formula for a centripetal force, it is mv square upon r. Here m will be the mass of that particle which was moving, which will be equal to Fb, we know it is equal to qvb. You will notice we are only taking the magnitudes here because we are not interested in the direction for now. So mv square by r equal to qvb. From this you can get r will be equal to mv upon q into b. So this expression gives the value of the radius. So we get the radius of that particle, radius of that path will be equal to mv upon qb. Now if you remember, when a particle is performing a circular motion, we can find the angular frequency omega, and we know that v is equal to r omega. Okay, so substituting this value over here, we can write r is equal to m r omega upon qb. Okay, cancelling r, you actually get omega is equal to qb upon m. Okay, so the angular frequency of that particle, it does not depend on the radius. Okay, you can see angular frequency omega is only given by qb and m. So higher the magnetic field, higher will be the angular frequency. How many rotations it will have will actually not depend upon the radius. This is something, this particular principle we use in the phenomena, in the construction of cyclotron. But of course that will be a later topic. But make sure that you remember this formula, that is omega equal to qb upon m. This we will be using when we learn about cyclotrons. Okay, I hope all these concepts were understood. Many concepts I tried to cram in one video, but I hope you were able to understand them. Now make sure that you go through the textbook. Okay, read all the topics, because very nicely all these things have been explained in the textbook, right? So you will get a much better understanding. Now in the next class, we are going to talk about the concept of velocity selector, and we'll talk about all important cyclotron. From exam point of view, these things are very important. Okay, so make sure you go through the textbook. If there are any doubts, make sure to ask. Thank you.